Good evening, sir.
Yes, please. Good evening.
Yes, sir. Good evening.
Yes, let me start. Basic introduce yourself.
Yes, yes. Myself, Ayush Aher. I had done my 10th from PVSS Sainiki School and my 12th from SHGM College. So both of these were affiliated to the Maharashtra State Board. And after that, I had done my BSc from SHGM College, which was affiliated to the Savitribai Phule Pune University. And after that, I had done my masters from Dr. B.R. Ambedkar National Institute of Technology. And I had done my project in enhancement of mechanical and the durability properties of cementitious matrix upon incorporation with silicon nanoparticle and the graphene oxide.
Yes, good. Yes, लास्ट डे हमने कौन कौन से टॉपिक डिस्कस किए थे?
सर हमने सॉलिड स्टेट और केमिकल बॉन्डिंग करा था सर उस टाइम.
Yeah, next move on OMC. Yes, OMC interconnected motor. Yes. What the main application of OMC?
Yes, yes, sir. The basically the organometallic chemistry is basically the mixture of organic and inorganic chemistry basically, and it has a lot of advantages basically. For example, the various reagents are basically the Grignard reagent are basically the organometallic reagent. If you take example of Grignard reagent or the Gilman reagent, so these are basically the organometallic compounds, and the many catalysts which are used in oxo process or the Monsanto acetic acid process or the Wilkinson catalyst, they are also the organometallic compound. And also the various compound like tetraethylene lead is used as the anti-knocking agent in the fuel basically, in the gasoline. And some of the organometallic compound are also act as anti-cancerous and is used for the treatment of the patients. Yes, sir, that's all.
Yes, good. What the difference between metal carbonyl and metal nitrosyl?
Yes, yes, sir. Sir, the metal carbonyl basically, in the metal carbonyl, the metal is attached to the CO group basically, and in the metal nitrosyl basically, the metal is attached to the NO group. So in case of the metal carbonyl here, so the CO group does not show any fluxionality. So CO will always give the 2 electron in case of the metal carbonyl. But in case of the metal nitrosyl, here the CO has the preference, the NO has a preference whether to act as fluxonial character, whether to act as a bend or the linear. In case of the linear, NO gives 1 electron, and in case of the bend structure, it gives the 3 electron basically. And basically the NO, the free NO has a value nearly up to 21,085, and the free CO has a value nearly 21,025, near that. And in case of the metal carbonyl, they will show the 13C NMR, but metal nitrosyl will not show that if they are not containing any carbon containing compound.
Yes, good. What's the difference between 18 electron rule and ENA rule?
Yes, 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 sir. So basically, the 18 electron rule and the effective atomic number rule here basically. So in case of the 18 electron rule, here the sum of all the electron, including the metal and that of the ligand, should come to the 18 here. So that if it comes to the 18, we call it as the stable compound basically. And in case of the EAN rule, here basically we calculate all the electron. In case of 18 electron rule, we calculate only the valence electron. But in case of the effective atomic number rule, we calculate all the electron. For example, if you take the example of iron, in case of iron here, so for the 18 electron rule, we take here 8 electron, which are the valence electron basically. But in case of the EAN, we take here 26 electron for the iron. And in case of the EAN, all the sum should come to the number of electron, which is the electronic configuration of any noble gases basically. So in EAN rule, we have to calculate, we have to know the atomic number of all the noble gases here. And in case of EAN rule, we should also know the atomic number of all the compounds. But in case of 18 electron rule, there is no any need to remember the atomic number. But in case of 18 electron rule, sometimes the 16 electron complexes are also stable. For example, if you look at the Wilkinson catalyst, which is the 16 electron or the Vaska complex, so they are stable, but in case of the 16 electron only. And so the 18 electron rule is more easy as compared to the EAN rule, because the main disadvantages of the EAN rule are that we have to remember the atomic number of that element as well as the atomic number of the noble gas configuration.
Yes, good. What is phosphines? What are the main uses of phosphines in OMC?
Yes, yes. So, so the phosphines are basically the various types of ligands which are used in the organometallic chemistry. So if you take the simple structure of phosphine, which is the simple ligand, which is PPS3P, it is basically the triphenyl phosphine. It gives the 2 electron, but there are also some phosphines. For example, if you take the example of bis triphenyl phosphine methane, bis triphenyl phosphine methane. So it basically acts as a bidentate ligand here, which form 1, 2, 3, 4, 5, 1, 2, 3, 4 membered ring. And if you take the example of this ligand, which is basically PPS3, it is basically bis triphenyl phosphine ethane. So here we call it as DPPM and DPPE here in the short form, triphenyl diphosphine. Yes. And sir, some of the binyl basically R binyl or the S binyl are basically also the phosphines only. So they are used as the selective reagent for the specific configuration. If we are required, for example, R group, so we use the specific binyl for that. So these are the structures of the binyl basically. Here we are having any phenyl group, which is having PPS3, and basically it is like yes, like this matlab somewhat this R binap or S binap have structure like this somewhat. So the phosphine have the different so the phosphine have the capacity to form the different type of ligands. Yes, sir. And it can also act as it can also act as asymmetric catalyst also, sir. Yes, sir.
Yes, good. What is metal carbines and carbines?
Yes, sir. Metal carbine.
Metal carbines
Yes,
and
sir.
carbines, what is the difference?
Yes, yes, sir. Sir, the metal carbine I had not studied yet, sir. Metal carbine. Sir, that part was remaining by me, sir. Metal carbide.
You look them, you have to study. Metal carbide.
Yes.
Metal carbide.
Yes, sir. I had studied, sir, that.
Yes, yes, sir.
But karna. So basically, the metal carbine is basically the two types. So one is the shock carbine and another one is the Fischer carbine, basically. So here we can see the properties of these two different carbines. So first one is the, for example, I take here Fischer carbine. Fischer carbine. And second that I will take is the shock carbine here. So here the shock carbine is basically the triplet carbine. If you take shock carbine is firstly, it is a triplet carbine, basically. Triplet carbine. It is a nucleophilic carbine. It is the sigma donor, basically. The ligand attached to it are basically the sigma donor. Another one, the shock carbine is a linear carbine, basically. And if you take the example of the Fischer carbine, so the Fischer carbine are basically the singlet carbine. They are electrophilic. Basically, pi donor ligands are attached to it, and they are non-linear, basically. Linear. And in case of the shock carbine here, basically the metal that are used are in high oxidation state. High oxidation state. For example, tantalum, which is in high oxidation state. And in case of the Fischer carbine, we use the metals which are in low oxidation state. For example, the metal that we use in Fischer carbine are iron, cobalt, molybdenum, chromium, and tungsten that we use in the Fischer carbine, basically. And if we look at the structures of these two compounds, so in case of Fischer carbine, the shock carbine, the ligand attached are somewhat bulky ligands are attached to it, basically. So here the shock carbine is electron rich carbine. Even though here the metal is having higher oxidation state, it is electron rich carbine. And this is the electron deficient carbine.
Yes, good.
And here we can look at the structures of the carbine, basically. So it is like somewhat like this here in case of the Fischer carbine. So here somewhat bulky like group is attached in case of the Fischer carbine. But in case of the shock carbine here, basically we are having a pi donor group like this. Basically we can see like this. Here is another ligand here. Here we can have cobalt and the two simple ligands here. So here what happened? As it has the high oxidation state, high oxidation number. Yes, so that much only. Look at the structure.
Yeah, next is what the difference between hapticity and denticity?
Yes, yes. So basically the denticity and hapticity is completely the different terms. Here basically, if you talk about firstly about the denticity. So denticity here. So the element can have basically one or two denticity or more than that. So basically in the single ligand, basically for example NO3. So this NO3 can act through one of the donor atom or through both the donor atoms. So if attached through only one of the donor atom, then we call it as the monodentate. And if it donates from its both the oxygen atom, then we call it as the bidentate ligand, basically. So the denticity is basically we see when ligand donates its electron into the vacant orbital of the metal basically. So we call it as the denticity. And in case of hepticity basically, so the pi electron basically of any of the cyclopentyl or any of the aromatic ring or anything which donates its electron to basically to the metal atom. So the hepticity is basically the continuous process basically. So hepticity changes when we want to do any addition, but the denticity not change when we want any addition. So hepticity changes in case of associative or the dissociative mechanism, but the denticity never changes here. And the hepticity always tries to go from 3 to 5 one. So it is continuous process, and it will always like to go from eta 1 to eta 3 to eta 5 basically. Yes.
Yes, good. Next is phlogistonal behavior from temperature, low and high. What the region? What the application of
Yes.
in OMC?
Yes, yes. Sir, the phlogistonal behavior is basically shown when we are having the higher temperature. So, for example, if we are having any compound basically, which is like this. For example, if we are having any compound, here the fluorine atom is attached here. So at low temperature basically, at a very low temperature basically, low temperature, so it will show the more signal, because here this bond will not rotate. For example, in at very low temperature we will have only 1 2 3 4 5 signal in case of very low temperature. But in case of very high temperature, here we see one. So sorry, we can put it here. So we see here the 4 signals in case of very low temperature. But in case of high temperature, here what happens, this bond rotates here, and here we see only the 2 signals at very high temperature. Because here this fluorine atom changes its position, and this all hydrogen becomes somewhat equivalent type. Yes, sir. That's all. So basically at a higher temperature, we see the less signals of hydrogen as compared to the lower. At low temperature, there is no any rotation. So so here the hydrogen, we get the more signals of the hydrogen, sir.
Yes, good. Next is what the difference between metal cluster, carbonyl cluster, carbide cluster? Explain one by one.
Yes, yes. Metal cluster, oh sir. Carbonyl cluster.
Carbide cluster.
Carbine cluster. Sir, basically the metal cluster basically does not contain any other ligand. So in case of the metal cluster, for example, we can take the example of Pb5 2 minus or Sb5 2 minus. So these are basically only contain the metal atom. And here the metal clusters basically have many uses in case of catalysis, drug delivery, or it has a wide application here basically, the metal cluster. And here the carbonyl cluster here, in case of carbonyl cluster, uh, the ligands are basically the carbonyls basically, which are the ligands for the metal basically. So we can see any structure which is like here, the bridging ligand is CO here, for example, and here the CO ligands are attached to it to form the 18 electron complex here. So these are basically the carbonyl clusters which contain the CO ligands basically. So to form the 18 electron, uh, 18 electron valence electron of this rhenium basically, 7 from rhenium, we're going to pick 6 from it, 1 1 1 3, so 16. So here for example we can take here one more, means 4 CO here, 4 CO here. So these types are basically the carbonyl cluster. And in case of the carbene cluster, sir, I don't know about it, sir, carbene cluster.
Carbonic carbide cluster. Carbide.
Yes, sir. Yes, sir.
No problem, you look them. Next, move on homogeneous, heterogeneous, and hydroformylation of alkenes. Explain one by one.
Yes, 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 yes. Homogeneous and
Heterogeneous, catalyst,
heterogeneous.
and hydroformylation of alkene. Baker process. Explain one by one.
Yes, yes, sir. Sir, basically, in case of the homogeneous catalysis, the metal and means all the reactant or the catalyst and all the reactant are in the same phase in case of the homogeneous catalysis. But in case of the heterogeneous catalysis here, the metals and the catalyst and the reagent are in a different phase in case of the heterogeneous catalysis basically. So if you take the example of the homogeneous catalysis, basically we are having the example of Wilkinson catalyst, or the oxo process, that is the oxo process is basically the homogeneous catalysis. Oxo process, or we can take the Monsanto acetic acid process. And in case of the heterogeneous catalysis, basically we can take the example of the Ziegler-Natta catalysis. Ziegler-Natta catalyst.
Yes.
Yes, sir.
What
So
the
here basically,
yes, yes.
yes, yes, yes. Yes, you can ask.
What the application of Ziegler-Natta catalyst?
Yes, sir. Sir, the Ziegler-Natta catalyst is basically used for the formation of the polymers, the long chain polymers from the small monomers, sir, basically. The different type of polymers are formed through the Ziegler-Natta catalyst, which is basically the TiCl3 plus AlAt3 is basically the Ziegler-Natta catalyst here. Yes.
Yes, good. Next is hydroformylation of alkene Baker process. Explain.
Yes, yes. Hydroformylation of alkene Baker processes, sir. Yes. Yes, sir. Sir, in case of hydroformylation reaction, basically here we are having any compound like this, alkane, on which we use the reagent like CuCl4 2 minus, and we get the hydroformylated product, which is CCH2 C double bond OH. So so here we can see here basically this copper, which is having CuCl4 2 minus, so 9 plus 2, that is 10, 11 electron plus 4 plus 2, 15 16 17, 17 electron. So here is basically the PD basically. Here is not CO, that is the. So here we are having 10 electron from PD, 4 electron from here, and 2 electron. So it is basically the 16 electron complex. So here what happened? PdCl4 basically. So here one of the here this alkene coordinates to it basically. So it is basically firstly the 16 electron complex. After that, the alkene coordinate to it. Then it becomes the 18 electron complex. After that, the 18 electron complex. After that, here what happens? Water attacks from this site here basically. When water attack at the same time here, this chlorine leaves from here. So here we get the complex like this: PD, Cl, Cl, Cl. Basically, it attacks from here. So here we get PD, Cl, Cl, CH2, R and H. So this type of complex we get. After that, and here is basically the water attached to it. So here this oxygen lone pair goes down here, and this hydrogen atom basically shifts here, and this bond breaks here. Basically we get PD Cl3 plus R, C double bond O H, and sir, I have to revise it properly, sir. I'm not able to recalling it now correctly.
Okay, no
Not that
problem.
much.
Yes. Next is metathesis. What is metathesis? What the main application of metathesis?
Yes. Sir, basically, we can take the example of the Grubb catalysis basically. So the Grubb's catalysis is also the type of the metathesis reaction here basically. So here we can see the different type of complexes, for example, which can couple to each other through the metathesis reaction basically. So for example, if we take the example of if you take any example basically of alkene like this PD, so it is having the +2 oxidation state basically here. So after metathesis, what happened? This PD leaves, and this structure becomes like this. So it is basically the coupling here for metathesis, the exchange of ligands. Sir, I have to read it, sir, again. Metathesis.
What is Mingo's rule? Mingo rule.
Yes, sir. Sir, Mingo's rule is basically is basically the nucleophilic attack on any of the system. So it is also known as the DGM rule. So which states us that, for example, if we are having the two systems, so first one is the closed system, and second one is the open system. So the attack will preferentially go on the open system basically. And the second rule that it states that, here that if we are having any even system and any odd system basically, so the attack will firstly go on the odd system basically. And the third rule that it states here, if we are having any electron withdrawing group basically, which is attached here electron withdrawing group, then the attack will go in. If we are having any electron donating group, then attack will go to the, not to the terminal side, but it will go inside. But if we are having any electron withdrawing group basically which is attached to our compound which to be attacked here, then attack is at the terminal side basically.
Yes. What is isolable segment?
Yes, sir. Sorry, in case of the isolable basically the arrangement of orbital is basically the same, and the valence electron as well as the arrangement of orbitals which are in that complex is basically the same. For example, if we take the example of CH3 basically, so it is having the valence electron that is carbon which is having 6 plus, which is having the 4 valence electron basically, and the hydrogen which is having the 3 valence electron, 7. So here are the 7 electron basically. So this is isolable with any of the complex, for example, which is having the 17 electron rule. We can take example as MnCO3 basically. So it is having 5 plus 2, 7 plus 6, 8, 9, 13. So here we can take 4, which is basically 8 plus 7, 15. So here we can take 5 basically, 10 plus 7, 17. So this complex will be isolable to the CH3 basically. So in case of isolable and analogy basically, the orbital arrangements and the valence electron are same basically, means are of the similar type basically.
Yes, good. Next, move on. Coupling reaction and cross coupling reaction. What the difference and what the main application of these one?
Yes, yes. Coupling reaction and cross coupling. So basically, the all the coupling reactions which we study, like the Suzuki coupling or the Hague coupling or EMA coupling. So all these are the cross coupling reactions basically. So the cross coupling reaction, so the cross coupling reactions are the only the type of the coupling reaction here, only the one part of the coupling reaction. So in the coupling reaction basically we couple the two different groups which are not possible by the ionic mechanism basically. So by ionic mechanism it is not possible for us to couple any of the group to our substrate molecule without changing its configuration. So so it is very difficult. But in case of coupling reaction, we can easily couple any of the organic substrate to our reagent, to our organic substrate basically. We can couple any group to our organic substrate. So the coupling reaction are basic, the cross coupling reaction are basically the part of the coupling reaction only. So we can see any of the reaction which is, for example, we can take one example here, that is the, for example, we can see the EMA coupling, for example. So here we are having CH3. Yes, I have to see the examples also. It is basically, I like this.
Yes, good. What the relation between cross coupling and coupling reaction with reaction mechanism? Any relation? Reaction mechanism? What the application?
Yes, sir. The coupling reactions are the part of the reaction mechanism only. So the coupling reaction are basically studied in the organic also and in inorganic chemistry also basically. So in case of coupling reaction, we form the bond with the carbons only. So so the coupling reactions have the many similarities with the organic reaction basically. But in case of coupling reaction, we can form the carbon-carbon bonds basically. But in case of the organic reactions, it is very difficult for us.
Yes, what the main application of reaction mechanism?
Yes, the main applications of the reaction mechanism. So the reaction mechanism is basically the flow of the electrons basically from the or the detailed description of flow of electron from the reagent to that of to that of product basically. So from the reaction mechanism here, we can get a clear idea that how the reaction is going on and what the different byproducts will form. So whether these byproducts are harmful to us or not, so that we can take that proper precautions while applying that reaction in lab or while operating that reaction in the lab. And also in case of the reaction, studying the reaction mechanism, we can get the idea about the different conditions like temperature, pH that we should maintain while the reaction is going on. And with the help of the reaction mechanism only, we get the idea or we get the clarity that what kind of reagents that we can use to eliminate the more steps basically. In the reaction basically, the if the number of the step increases, the yield of the product decreases here. So the pharma industry wanted to decrease the number of the steps of any reaction. So if we are having the clear idea of the reaction mechanism, so it helps us to use the different catalyst or the reagents so that the maximum number of the steps can be reduced to get the good yield. And basically in case of the reaction mechanism, we can also get some idea about what the type of intermediate that will form in the reaction, sir.
Yes, good. What the difference between addition, elimination, substitution, rearrangement reactions?
Yes, yes, sir. So in case of the addition reaction, basically, so the two different groups attach adds to the organic substrate basically. So in case of addition, the two groups add basically to any of the unsaturated system. In case of the substitution, basically, so there are basically the one group is replaced by the another group, which is having the higher nucleophilicity. And in case of the elimination reaction, basically the two groups are eliminated from the our substrate molecule to get the desired product or the unsaturated product basically. And in case of the rearrangement reactions, basically, uh, here in case of the reaction mechanism, the molecular formula remains the same, but the carbon skeleton basically rearrange itself to form the different products. For example, there are many rearrangements like Dinon-phenol rearrangement or the Wagner-Mervin rearrangement or the or the Suchmidet rearrangement or so there are the lot of rearrangement. And in case of the addition reactions, basically we will have the nucleophilic addition as well as the electrophilic addition. So in case of the electrophilic addition, for example, we can take the group like Br2, which is adding to the any of the alkane system. And in case of the nucleophilic addition, the attack is, for example, going on the carbonyl group. It's basically the type of the type of the nucleophilic addition reaction, sir.
Yes, good, good. Next,
Yes.
also one question. Polymerization,
Yes.
oligopolymerizations, and ferrocenes. Interconnected and
Yes.
applications. Yes.
Yes, yes, sir. Oligomerization, yes.
Polymerizations.
So polymerization is basically so the polymerization is basically from the small unit of any monomer we form the large macromolecular compound which we call as a polymer basically. So oligomerization polymerization